Continuing on with Hartree-Fock, let's look at the energy of the helium atom. So again, our Hamiltonian has 5 terms. We have kinetic energy of electron 1, kinetic energy of electron 2, attraction of electron 1 to the nucleus, attraction of electron 2 to the nucleus, and the repulsion of the 2 electrons from each other. Our total wave function is a product of these two one-electron wave functions. This is an approximation. This is the orbital approximation, saying that we can have a wave function which is a product of these one-electron orbitals. And we've defined Hamiltonians for each electron such that we can separate this Hamiltonian into something which depends on only electron 1 and then only electron 2, that we get a separate kind of mini Schrödinger equation for each electron. This isn't exactly true because this 1 over R12, this electron repulsion operator, is not separable. But the way we define this effective electron repulsion operator for each electron makes it separable. So we have our effective Hamiltonian for, let's say, electron 1 is its kinetic energy, its attraction to the nucleus, and its effective repulsion from the other electron, or if there were multiple electrons, the other electrons. And this effective repulsion potential is the integral over all space of psi star of the other electron, electron 2, times psi of the other electron. So this forms the density, the electron density of the other electron, times the 1 over R12 operator times the Coulomb operator. And that's integrated over all of space for electron 1. So at each point in space, you can tell how much electron 1 feels the average charge density of electron 2. That's not the exact 1 over R12 and 1 over R12 operator. There we go. That's not it exactly, but that's a decent first approximation to how electrons repel each other. This is called the mean field approximation, doing it like this. Okay, then we get our little mini Schrödinger equation for each electron. The effective Hamiltonian times the orbital equals the orbital energy epsilon I times the orbital wave function for that electron. Okay, so looking at the energies, let's now define another operator, which is a one-electron operator called little h for, let's say, electron I. And that is going to be the kinetic energy for that electron, minus 1/2 del squared I, minus its attraction to the nucleus, helium nucleus, charge of 2 in atomic units, over Ri. Okay, then we can define a one-electron energy, the energy that only depends on that one electron, and that would be the, let me do a different color here, and that one-electron energy would be the integral over all 3 spatial dimensions of that electron times psi star Ri times this H operator, the kinetic energy and the attraction to the nucleus, the one electron operator, times psi Ri. Okay, so that's the standard expectation value of that operator. Alright, then now let's define what we're going to call a Coulomb integral, what I'm going to call J here, or J12, in this case acting between the repulsion between electron 1 and electron 2, what that energy is. And that is going to be the integral over spatial coordinates of electron 1, spatial coordinates of electron 2, psi star of R1, psi R1. So this product here forms the electron density of electron 1 times the Coulomb operator, 1 over R12, times psi star of R2 times psi of R2. And this product, psi star R2 times psi R2, forms the electron density of the second electron. So we have the electron density of electron 1, electron density of electron 2, interacting through the Coulomb operator and integrated over all space for both electrons, gives you the energy you get in the mean field approximation for how much these electrons repel each other. Again, this isn't the exact R12 operator, but in a mean field approximation, in an orbital approximation, this is how we're going to treat this electron repulsion. Because this is the source of the real difficulty in quantum mechanics for many electron atoms and molecules is these 1 over R12 operators for various electrons. Okay, so if we want to calculate what the orbital energies are, what the energy of a given electron orbital is going to be, we're going to have the integral over the entire domain of its wave function, the 3 spatial dimensions of that orbital, times the complex conjugate of that orbital, psi star, times your effective Hamiltonian operator for that electron. It's the mean field and its 1 electron terms. And that's acting on the wave function. Again, that's another standard expectation value. That's the expectation value of this effective Hamiltonian operator that's acting on this electron 1. And that gives us these orbital energies. And based off of the type of nomenclature we've shown right here, if you chug through what that gives out, that is going to be, for our orbital energy of electron 1, we're going to get its 1 electron terms, kinetic energy and attraction to the nucleus, plus the effective mean field is going to give us J12. It's going to give us that Coulomb integral there. So it's attracted to the nucleus, it has kinetic energy, and it's repelled from the other electron. That's its orbital energy. Then for electron 2, we similarly have the expectation value of its attraction to the nucleus, its kinetic energy, and it is also going to have the mean field of being repelled from electron 1, which J12 is going to be the same as J21. So it's also going to be that. So these are the orbital energies of each electron. So what is the total energy of the helium atom? Well, the total energy of the helium atom is if we take the expectation value of our total Hamiltonian and all of these terms here, and that, in this type of approximate sense, is going to be the kinetic energy and nuclear attraction of electron 1, H1, its 1 electron terms, the 1 electron terms of electron 2, its kinetic energy and attraction to the nucleus, and the repulsion of the electrons from each other, the 1 over R12. And you'll notice that this is not equal to the sum of these two orbital energies, epsilon 1 plus epsilon 2, which those two orbital energies equal H1 plus H2 plus 2 J12. You'll notice if you sum the orbital energies, you're going to double count the interactions of electrons from each other. You're going to double count those repulsions. So in Hartree-Fock theory, the total energy of an atom or a molecule is not going to be the sum of the orbital energies. That's going to double count these electron it's going to double count these electron repulsion terms based off of how we have defined these 1 electron Hamiltonians here, so that they can be separated and solved through the self-consistent field procedure, which we discussed last time. Okay, so you might ask yourself, well, what's the benefit to defining it this way if if the sum of our orbital energies doesn't end up being the total energy of the total helium atom? Well, there's a benefit to that, and we can discuss that now. So you'll notice if we have the orbital energy for electron 1, that is equal to the total energy of the atom here minus the 1 electron terms. So if we take the total energy of the helium atom and we subtract away the 1 electron terms from electron 2, we get H1 plus J12. And that is the orbital energy of electron 1. So what would be this H12 here? Well, if we removed electron 1 from the atom, then the energy we would lose would be its 1 electron energy. We would lose its kinetic energy and its attraction to the nucleus, and we would lose this repulsion here from the other electron. The only energy terms we would have left would be the attraction of electron 2 to the nucleus and electron 2's kinetic energy. It would just be these terms left. So if you think about what this means and rewatch that to get a grasp on what I just said there, you'll find that this is equivalent to the ionization potential for that given electron. So we have that the ionization potential is approximately equal to the orbital energy for a given electron. So we can interpret these electron orbital energies as the energy it would as approximately the energy it would take to remove that electron from the atom or from the molecule. So if I have an orbital energy of -2 Hartrees for a given electron, then the ionization potential for that electron is 2 Hartrees. It would take 2 Hartrees of energy to remove that. Now that is again an approximation because the 1 electron terms of electron 2 would relax and change their value if electron 1 was removed. But in general, this type of approximation here, which this statement right here, this equality is also sometimes called Koopmans Theorem. This Koopmans Theorem actually turns out to be a pretty good approximation in practice. And if you do Hartree-Fock calculations on atoms and molecules, you'll find that the ionization potential for atoms and molecules is usually not that different from the type of approximation you would see here.